Hi, everybody. So how many do we have? 18. Should I wait a few more minutes? I'll wait till we get to 20. Okay, anyhow, it's 11:30. Let's start on time. Share screen, whiteboard. Okay, so nobody sent me any mean emails indicating you were totally lost, so I will assume that people more or less understood what was going on. But I'm going to backtrack just a little, and I want to be totally clear what problem we're working on. Okay, so the idea is we have a network. Let's use a better color. We have a large network of neurons. And the neurons come in two flavors: excitatory neurons. So generally you try to use red for excitatory. And inhibitory neurons. And they're connected. So lots of connections. So red, excitatory, green, inhibitory. And there are lots of neurons. So a typical network, say in cortex, I mean, even there like V1 contain hundreds of millions of neurons. They're also, each neuron makes about, So each neuron makes about 1,000 connections. So that means each neuron receives about 1,000 excitatory connections or excitatory inputs. And about inhibitory inputs. Okay. And the fact that it's 1,000 is important, okay? So each neuron receives a lot of input, both excitatory and inhibitory, and that affects circuit dynamics. Okay, what we want to know, eventually what we want to know is maybe how each neuron evolves, but what we're trying to find out now is just how the average excitatory and inhibitory firing rates evolve, okay? And so what I did yesterday was take one of these neurons, let's say an excitatory one, and look at its input. So excitatory neuron here, it's getting input from lots of excitatory neurons and lots of inhibitory neurons, okay? So I keep pausing because the bar is, there we go. The transcription bar. So you're getting lots of inputs from excitatory neurons, lots of inputs from inhibitory neurons, okay? And the idea, because there's so many neurons, all we care about is the average firing rate of all these neurons. See, the average excitatory firing rates and the average inhibitory firing rate. And if we know that, because they're getting so many inputs, and that's something I'll make a little more quantitative later, the output of this neuron, its firing rate nu EI, equals some function that depends only on the average excitatory and average inhibitory firing rates. Okay, so this is our big assumption. And this is the equilibrium firing rate. Okay, so that's important. What it means is if basically the average excitatory firing rate is nu E, average inhibitory firing rate is nu I, and somehow you held these fixed, this postsynaptic neuron I, would have a firing rate determined only by this gain function psi. Okay, and because excitatory neurons are excitatory, the higher the average excitatory firing rate, the higher the firing rate of this neuron. The higher the average inhibitory firing rate, the lower the firing rate of neurons. This one. Okay. So psi E, you should sort of a good way to think about it as so this. Oops. So this quantity here, a good way to think of it is sort of 100 hertz is more or less the maximum firing rate of any neuron, is a prefactor, times some sigmoidal function of, let's say, it's not a bad approximation, nu E minus nu I minus some threshold. Okay? So it's the difference in firing rate that matters. If nu E is higher than nu I, the sigmoid firing rate goes up, and this is maybe around 3 hertz. Maybe less, maybe 5 hertz. Let's make it 5 hertz. Maybe. So when this number here, this difference is 5 hertz, this may be exaggeration, sigmoid of 0 is 1/2. The neurons would be firing at 50 hertz. So excitatory neurons are firing at 5 hertz faster than inhibitory neurons. This neuron's firing like mad. Okay. On the other hand, if the excitatory and inhibitory firing rates are the same, this is a sigmoid of minus 5 hertz, and it's not that much. So by the way, sigmoid function, so sigma of x equals 1/1 plus e to the x. Okay. So it's just sort of a function that goes from 0 to 1. Now, so this, remember, is an equilibrium firing rate. And so we're going to add dynamics. It's kind of a hacky way to do it, but we're just going to say, okay, tau E d nu EI dt equals psi EI of nu E nu I minus nu EI. And all this says is if the firing rate is below its equilibrium value, it's going to go up, right? It's getting too much input relative to its firing rate. If it's below its equilibrium value, it's going to go down, okay? So this is a rate of change of firing rate, and that's the time constant. And now we can average both sides. We can just average 1/n, the sum on I of this quantity here, this quantity here, and this quantity here. And remember, by definition, 1/n, actually we should number inhibitory, excitatory firing rates, the sum on I of nu EI equals nu E. This is a definition. Okay, it's a definition of the average firing rates. We average everything and we get tau E d nu E dt equals psi E of nu E nu I minus nu E, and also psi E of nu E nu I. By definition is 1 over NE, the sum on I of psi EI. Okay? And of course, we have another expression for inhibitory neurons, d nu I dt equals psi I of nu E gamma nu I minus nu I. So these are the famous Wilson-Cowan equations. And what we want to do is understand the behavior of our network that obeys these equations. So we basically, what we've done is we've taken our network here and we've reduced it to a sort of a single network containing two populations of neurons. Two populations of neurons. There we go. We have excitatory neurons, E, inhibitory neurons, I, and they're coupled to each other and to themselves. So we replace a giant network with maybe hundreds of millions of neurons with a network of two neurons, a giant excitatory neuron and a giant inhibitory neuron. Okay? And what I want to do today is finish off evaluating, figuring out what the dynamics of these equations looks like. And I started that last time. I'm going to go over it again in a more formal way. So there's a very formal and incredibly useful approach or method for dealing with dynamics, two differential equations in even nonlinear differential equations, if there are only two of them, and it's called milk line analysis. And that's what I'm going to do now. Now, there's one more thing we need to know, which was kind of alluded to on this page, is these gain functions are kind of steep. Okay, so if you plot psi E versus nu E, it goes up to 100 hertz. Its maximum is about 100 hertz. That's about how fast neurons can fire. And it goes up in about, it rises pretty steeply. So this distance is 5 to 10 hertz. So when the average firing rate goes from, increases by 5 to 10 hertz, depending on the inhibitory firing rate, this neuron is going to jump nearly to its highest firing rate. Okay. So we're going to use this, so this is an important aspect of large networks of neurons. So in some sense, they're strongly coupled. Okay. Meaning not very big change in average firing rate has a big effect on each neuron. Okay, so let's go to let's write down our equations again. Tau E d psi E, d nu E dt equals psi E of nu E nu I minus nu E, and tau I d psi I dt equals psi I of nu E nu I minus nu I. So by the way, so neurons are also very sensitive to inhibitory firing rate. We plotted psi E of nu E nu I versus nu I. Assuming nu E was large enough so this neuron was firing at a high rate, it would actually drop down also very rapidly. So it's about 100 hertz. And this is about, again, 5 to 10 hertz. It actually may even be shorter for inhibitory neurons. Okay, so the gate functions are sensitive to both excitatory and inhibitory neurons. Okay, so this is a a set of nonlinear ODEs. In general, nonlinear equations can't be solved analytically, but we can get a lot of insight into them by null-Klein analysis, which is basically what we did last time. And it consists of two things. So let's take, the E null-Klein, excitatory null-Klein, is a solution to, it's a curve, wait, it's all points such that d nu e dt equals 0, which means nu e equals psi e of nu e comma nu I. And the I null-Klein is the same thing. Nu I equals psi I of nu e and nu I. Okay, so these are both curves. So these are both curves in nu e, nu I space. And their intersection, so intersection is an equilibrium. Okay, so if we find the curve, we find the equilibria, we can pretty much figure out everything there is to know about the dynamics. Not exactly, but certainly qualitatively. And so, I mean, this is a neuroscience course, but for my part, if you took away two things and you really absorbed them well, I'd be happy. One is how to construct null-Kleins and how to interpret them. And the other is basically how to use a central limit theorem, which we're going to get to maybe in this lecture, definitely in the next one. Okay. So all we have to do is find a couple curves. And given those curves, we can find their intersections. That gives us equilibrium. We interpret those curves, we know everything. Okay. So in general, so finding, from even this equation, which is sort of simple, finding the curve that is associated with that satisfies that equation is not kind of non-trivial, but there's a very intuitive way to do it. And basically it's hard to plot things in 2D, but it's easy to plot things in 1D. So if this is actually something I did last time. So nu I do it more formally, but if we fix the excitatory firing rates, then we just have a function of one variable, psi e of nu e with this fixed, and we can easily find graphically the value of nu e that satisfies this equation. Okay? So that's the plan. To find these curves, we're going to find them 1 point at a time. We're going to fix nu e, nu I, and find 1 point on this curve. So it goes like this. So here's, on this axis, I'll plot nu e, put nu e on this axis. I'm going to put psi of nu e comma nu I on this axis. And I'm going to plot this, I'm going to fix the value of nu I and plot this curve and look for intersections with the 45-degree line. So here's a line, nu e equals nu e. And then I want to plot on this axis, I'm going to pick some value of nu e. Let's say nu I equals 0 hertz. And I'm going to plot. So this is actually the regime I said was a bad idea last time, but we'll do it anyway. So this is nu I equals And remember, what we're looking for is psi of nu E comma nu I equals nu E. So this is a curve along which psi of psi E psi E of nu E comma 0 equals nu E. Okay? And there's 2 points. There's one at 0, one at intermediate firing rate, and here. And we're working a regime I told you not to work in last time, and we'll see why, where if a neuron gets, remember this is nu E. If the average excitatory firing rate of all neurons in the network is 0, meaning this neuron is getting no input at all, no excitatory input, no inhibitory input, it doesn't fire. Okay? So there's equilibrium here at this point. So this is the nu I axis. So at nu I equals 0 and nu E equals 0, there's an equilibrium. This point satisfies this equation with okay? If that's 0, that's 0, that's fine. There's another point here right here, also an equilibrium. And there's a point here. Okay, so we've found 3 points that satisfy this equation. To find another point, all we have to do is increase nu I, let's say to 1 hertz. And now when we do that, what happens? Basically, it just takes longer for the firing rate to go up. Okay, and we still have a firing rate at 0. This one is moved up, and this one is probably moved down a little bit. And so if this is 1 hertz, we have an equilibrium here, and here, and probably over here. Okay? And we can just repeat. We can keep increasing the inhibitory firing rate, and eventually we're going to reach a regime where that barely intersects and then eventually goes away. Okay? And each one of these is higher inhibitory firing rate. So this is 0 hertz. This might be nu I equals 1. Nu I equals 2, 3, 4, 5, nu I equals 6. And every time we do that, we can basically just what happened? So we always have a equilibrium along this axis. Increasing inhibitory firing rate doesn't do much, but along here, this shifts to the right. And when we fill out these curves, if we imagine filling out every single curve, we get something like this. Okay? And this over here is about 100 hertz. Okay? So this is the excitatory null climb. And do nu EDT equals 0. If we just sat there, we would stay there forever, as long as the inhibitory firing rates didn't change, okay? And of course, this is the excitatory neurocline, and this is part of the excitatory neurocline, okay? And so if d nu EDT is 0 here, on either side of this line, it has to change. It's positive on one side and negative on the other. And it turns out that it's kind of easy to see. Up here, d nu EDT less than 0, which means if you fix the inhibitory firing rate and starting here, you would go in this direction. And over here, d nu e dt is greater than 0, you go in this direction, okay? So using this analysis, and this again should be kind of intuitive, right? You're fixing the inhibitory firing rates, they're fixed. So if you start, oops, this always happens. So if you started over here, you started here, right? There's just too much inhibition relative to excitation and you get pushed towards 0 firing rate. The other end, if you start here, there's enough excitation relative to inhibition, excitatory firing rate's higher to push you to the right. Okay, so it should be kind of an intuitive picture. Now we're gonna do the exact same thing for the inhibitory nuclein. That's actually easier. So what we're going to do is we're going to plot again psi I, this time psi I of nu e comma nu I versus nu I. And over here, we're going to put our nu e nu I axis. And now we can do the same thing. Okay, so if nu e equals 0, what happens? Inhibitory neurons don't fire at all. So this is nu e equals 0. We also want to add, of course, the nu I equals nu I line. And we're looking for nu I equals psi I of nu e comma nu I. As we increase inhibitory firing rate, let's say, and so this corresponds to a point right here. So again, if the excitatory neurons aren't firing, inhibitory neurons aren't firing, and equilibrium is 0 firing rate. But now we increase nu e a little bit, say to 1 hertz. So nu e equals 1 hertz. Actually, I should do a little more accurate job with these nucleons. They should fall off kind of steeply, right? So this is nu e equals 1 hertz. And so that corresponds to a point right here. And then you can do the same thing. It's sort of simple. So nu e equals 2 hertz. And it's going to correspond to a point up here. Okay. So basically what we have is this point here is nu equals 2 hertz. And we get, we just follow this across. Sorry, nu equals 1 hertz. You follow this point across. Nu equals 2 hertz. We follow this point across. And we get a curve that looks like that looks like this. Okay. So this is inhibitory nuclein. Inhibitory nuclein is boring. It just goes up. Okay. And remember, d nu I dt equals 0 here. If you're down here, if not enough inhibition, d nu I dt, it's greater than 0. And if you're up here, d nu I dt is less than 0. Okay, so we have the excitatory nuclein is just kind of a boring line. It's probably not straight. It's got some curvature to it. And the inhibitory nuclein is much more interesting and has this shape, down and up. And now let's put them together. So we have Inhibitory, excitatory nucleon looks like this. We'll draw it like this. An inhibitory neuron is a line, we don't quite know where it goes, but let's say it goes something like this. Okay, and we can also put arrows here. And the arrows are pretty important. This is to the right. And this is to the left. Okay. And the arrows are the direction of trajectory. So now we can look at a typical trajectory. So first of all, if we start here, let's label these new E, new I. We start here. I drew these wrong. So remember, if there's high inhibition, we move to the left. If there's low inhibition, we move to the right. Okay. So high inhibition, excitatory firing rate drops. Low inhibition, excitatory firing rate increases. High inhibition, inhibitory firing rate goes down. Low inhibition, it goes up. So the arrow should make sense. So even if the nucleon construction didn't make sense, these should end up making a lot of sense. So if we start at this point, what happens? The inhibitory firing rate drops. The green arrow is pointing down. Actually, let's, this line looks more like that. The green arrow is pointing down. The red arrow is pointing left. We just go to the origin, which makes sense. If no neurons are firing, that origin is super stable, right? What if we start here? So this isn't, remember, this is an equilibrium, right? This is a nice low firing rate equilibrium with something we're looking for, but that point is actually unstable. If we start here, we move to the right and we're pulled up, but we just keep going up. So an incredibly important feature of these nucleons is you can't, so d nu I dt is 0 along here. So the closer you get, the sort of the less steep, the smaller these arrows are, and you can't cross in this direction, right? You can't go like that because at this point, d nu I dt is 0. So you can only be pulled to the right. Okay. And if we started, here, we would be pushed to the right and down. So we would end up going to the right and down. Oh man, what happened? Start here, we would pull to the right and down. We would cross and we would end up over here. If we start here, we end up over here. If we start here, we're pulled up and to the right, and we end up over here. So this is, and we're going to see this more explicitly, but this point, this is an unstable equilibrium. Okay. So this is, and so this point is stable. So this is stable. And this is stable. But this point here is unstable, which is too bad because that's a low firing rate. Okay, so so I want to recap because we get basically, this is kind of profound. Well, so there's actually, let me draw one more picture. And so remember, our goal was to get a low firing rate. You know, given these null lines, how can we do it? So it is actually possible but not that easy. So here's our excitatory null line. And if we draw our inhibitory null line like this, as we'll see, this can be stable. What happened? So remember, this is our axes. Oh man, sorry gang. Let's start over. So the excitatory null line looks like this. If we draw the inhibitory null line like this, so this point can actually be stable and low firing rate. However, this is not where you want to operate the brain, because it is some fluctuation that takes you back to this point where absolutely the basic network just never fires again. Okay, so this is pretty profound. So what did we conclude? So if neurons that receive no input don't fire. And remember, this is a standard picture of neurons that we learn about in our textbook. Then neurons can't robustly at low firing rate. You can build networks with spiky neurons that actually have this low firing rate equilibrium. But if you wait a little bit of perturbation, they'll always end up here. The network dies. Okay. How did we get to that conclusion? So remember, our starting point was, okay, we have a network of excitatory inhibitory neurons. We're going to model each one. A particular neuron gets lots of excitatory input and lots of inhibitory input. And because there's so many inputs, something we'll quantify later, its firing rate is basically a function of the average firing rate of these neurons. Okay, that's a reasonable assumption. And so then we added dynamics, which kind of makes sense. If basically the firing rate of this neuron is below its equilibrium value, its firing rate is going to increase. If it's above, it's going to decrease. Okay, we wrote down dynamics. These are the Wilson-Cowan equations. And I put the paper on the website. So we had these equations, then we constructed null lines, okay? And all we really needed to construct null lines was that these things were steep to get this shape, okay? And we'll see why we need the steepness later on. That's not so obvious here. And then we came to this rather profound conclusion without really doing much work, right? But of course, neurons in the brain do fire at low rate. And what went wrong? What went wrong is a standard picture of neurons, which they don't fire without input, okay? The truth of the matter is, if you stick an electrode, if you try to keep a neuron from firing, you can even take a neuron in the brain, inject massive inhibitory input into it, and eventually it just it'll fire. Turns out neurons do not like to be in a non-firing rate regime, okay? And what that does is it modifies in particular this curve, right? Because instead of starting at 0 and going like this, if neurons can fire without input, when nu equals 0, its firing rate actually sits up here, okay? So what I'm gonna do is, I'm gonna actually draw the picture of the null lines in that case, then we'll take a little break, okay? So we'll just switch over. So put nu E, psi E of nu E, nu I. Again, this is a 45-degree line, nu E equals nu E. And now we're going to write our first picture is this. So this is nu I equals 0. And what that means is that the only equilibrium when nu I equals 0 is a one-way up here. So we've lost the one at we've lost the one that used to live down at 0. Okay, so now we increase inhibitory firing rate a little bit. And again, nothing much happens. We get a point here. But eventually, a point appears at some firing rate right here. Okay, and as we increase inhibitory firing rate some more, we get a point here, point here. These points, of course, are moving up. And so the actual null line looks like this. This is the actual E null line in the brain. And the inhibitory null line now doesn't really matter, right? It may or may not have inhibitory neurons, but now, so this equilibrium, as we'll see, can be stable. Okay, and it's extremely robust. Right, basically this is the only equilibrium. Now, if it's stable, what that happens there, as we'll see, are there oscillations, but it can't crash down to 0. This is the only equilibrium in the system, okay? So in all we've done, so what did we do? So now the big difference, so neurons are spontaneously active. Okay, that's all we've added, and we get a very, very different picture. Okay, it's this picture versus this picture. Okay, and that's an important difference. And actually, when I first got into neuroscience, I realized this, and I did experiments in. So it's hard to say in the brain, of course, neurons get external input from elsewhere. But I did experiments in tissue culture where neurons are isolated. And I did indeed find, and the prediction is, because they fire at low rate, the neurons had to be spontaneously active, and they actually were, which is kind of nice. So at least I believe this theory. Okay, let's take about a 5-minute break. I'll be around if you guys have questions, and then we'll look at stability analysis. which is basically, we'll finish off what we did last time, and then we'll go on to make some of these approximations and assumptions a little more rigorous. And feel free to ask any questions in the next 5 minutes. Okay, let's start up again. I will have to stop share because, oops, videos. Stop share and start sharing. Okay, so our starting point is these null lines. Salutary null line looks like this. And the inhibitory null line looks like this. And so this point, the question is this point unstable or unstable? So first of all, the directions of flow is that way and toward this. So we started here, we're pulled to the right and up. And so it looks like if this point may be stable, it also might be unstable, right? It could be that we go up and we actually end up just going around and around in a limit cycle. So it looks like, so the options, so from drawing pictures, so it looks like equilibrium is either stable or there's a limit cycle. Or if it's unstable, there's a limit cycle. And there actually is a theorem about 2D dynamics saying that pretty much that has to happen. I mean, it can't, given that things can't go off to infinity, the only possibility is a limit cycle. And limit cycle means oscillations. Okay, and we'll get to that in a second. But what we want to do is now is analyze the stability. And for that, so we did basically, that is, I won't go through that because I started last time. So we have tau E nu E dt equals psi E of nu I minus nu E, and tau I d nu I dt equals psi I of nu E comma nu I minus nu I. Remember what we did? We let nu E equals nu E0 plus delta nu E, and nu I equals nu I0 plus delta nu I. We did a first order Taylor expansion, and what we found was that tau E the delta nu E dt and tau I the delta nu I dt equaled psi E comma E minus 1 delta nu E plus psi E comma I delta nu I. And then we had psi I comma E delta nu E, and then plus psi I comma I delta nu I, where the notation psi Q comma R is the finite partial of psi of nu E0, nu I0, partial of psi Q with respect to nu R0. Sorry. Back to nu, oh yeah, nu R0. Okay. So for instance, psi EI is partial of psi E with nu E0, nu I0, with respect to nu I0. Okay. So this is the equation we want to solve. And what we want to know is as time goes on, if nu E and nu I start off small, do they stay small? Okay, and what we're going to do is we're going to divide both sides by tau E on here, both this side by tau I, and write this as a matrix equation. Okay, so for those of you who know linear algebra, this should be pretty easy. For those of you who don't, it might be kind of hard. So we have d dt, have a vector, delta nu E, delta nu I, equals, we have a matrix, psi E minus 1 over tau E, psi I over tau E, and psi E comma I over tau I, and psi I comma I minus 1 over tau I, times delta nu E, delta nu I. I think I forgot a so these equations I derived last time, but they just basically come from linearizing this dynamics. Okay. So this has the form. So if we call this a 2D vector Z, I'm going to call this a matrix, call this A. Actually, let's call it J, because this is actually a Jacobian. What we have is dz dt equals A dot Z. And this has a solution, Z equals Z0 e to lambda t. Okay. I assume you guys know that, but I'm not really sure. So dz dt equals Z0 lambda e to lambda t. Differential expected t just brings out a 0, a factor of lambda. And when we do that, we get lambda Z0 e to lambda t equals A dot Z0 e to lambda t. And these, of course, we can cancel from both sides. And that implies the eigenvalue equation A dot Z0 equals lambda Z0. Okay. And again, if this isn't familiar, you need to brush up on linear algebra. We won't be using anything more sophisticated than this. They should all kind of make sense if you can take a derivative. So what we need to know is the eigenvalues of this equation, and the sign of lambda is what's important. Okay. So we're going to do this in general for a general matrix. So we have A dot Z0 equals lambda Z0. And lambda, to find lambda, it's determinant of A minus lambda times the identity equals 0. Again, standard result from linear algebra. And so we can write this as determinant of A11 minus lambda, A12, A21, A22 minus lambda. Determinant is A11 minus lambda times A22 minus lambda minus A12, A21 equals lambda squared minus A11 plus A22 lambda plus A12, sorry, A11, A22 minus A12, A21. And this you recognize as T equals trace, sum of diagonal elements, and this is D equals determinant. Okay, so we can write this as lambda squared minus T lambda plus a D, and that of course equals 0. That's how we find our eigenvalues. It's a quadratic equation. There are two of them. So we have lambda plus or minus equals T plus or minus the square root of T squared minus 4D over 2. So these are the eigenvalue equation, the two eigenvalues. And we want to know their sign. And particularly, we want to know the condition under which the sign of lambda is 0, less than 0. That's stable, or if either the lambda plus or minus is greater than 0. So we have lambda plus or minus equals T okay. So we want, so the conditions, so lambda or lambda plus for both lambda plus and lambda minus less than 0. So the reason we care about sign is because of this exponential behavior. So if lambda is negative, this decays to 0. If it's positive, it goes to infinity in large T, okay? So we care about, so it's only stable if lambda is, actually the real part of lambda is negative, because lambda can be complex. And so basically, let's start off with T squared greater than 4D, okay? So lambda plus or minus, draw it like this. So this is our lambda plane. So this is actually, let's say this is minus T. Okay, sorry, this is plus T. So this is T. So I deliberately drew T negative. And as we'll see, T has to be negative. And then it's plus or minus T squared minus square root of T squared minus 4D. So this is basically, so this point will be T plus the square root of T squared minus 4D. And this point will be T minus the square root of T squared minus 4D, okay? And what we clearly have to have is T plus the square root of T squared minus 4D less than 0, okay? So T is already negative, so it means we square root of T squared minus 4D is less than minus T equals plus the absolute value of T, right? We square both sides and we get T squared minus 4D is less than T squared minus less than T squared. Which implies D is greater than 0. So the conditions for stability, T less than 0 and D greater than 0, okay? So those you should kind of memorize. For 2D matrix, the trace has to be negative, less than 0 if you want it to be stable, and the determinant has to be positive. So if we go back to our matrix, the trace is the sum of these elements, and determinant is this, that times that, minus that times that. Okay? So I'm going to write that down. So for our problem, so T equals trace equals psi E comma E minus 1 over tau E plus psi I comma I minus 1 over tau I equals psi E comma E minus 1 over tau E. So psi, remember, is negative. As this is derivative of the gain function with respect to inhibitory firing rate. As inhibitory firing rate goes up, these psi's go down. So this is equal to minus absolute value of psi I comma I minus absolute value of psi I comma I plus 1 over tau I. So t less than 0 implies absolute value of psi is greater than psi E comma E minus 1 over tau E. So this turns out actually to make a lot of sense. So if we go back to our picture, okay, basically what it says is, actually I'm going to erase some of this. So if we started here, right? We started a point here. Remember, we're pushed to the right. But what this expression says, in some sense, either the inhibitory time constant is really small, or these gain functions are really steep. So that means, so this term tells us this term big means we're attracted very strongly to the inhibitory null line. Okay, so if we start here, that means we're pulled up really rapidly in this direction. And then we push to the right, we're pulled down really fast, okay? So that's basically fast, strong inhibition. It's what's needed to stabilize the fixed point, which kind of makes sense, right? You want the inhibition fast. If inhibition is really slow, so this is fast. So the black is fast, strong. Inhibition. If it's slow, then what happens, right? You push way to the right, and it takes a long time for inhibition to kick in, and you've gone way over here by that time. You said that in the limit cycle. So slow, not so fast inhibition. Okay. So for those of you who think about these things in terms of amplifiers, this is somehow inhibition of delayed feedback. The picture you should probably have versus time is, this is versus time. So let's say nu E is excitatory firing rate, nu E goes up. Okay, and then inhibition, which maybe started, is actually driven up as well, right? But with delay, inhibition goes up, and then that causes excitation to come down. Oops. The next bit, excitation comes down. Okay. Because inhibition goes up, excitation, oh man. Anyhow, I'll draw the whole picture. So excitation actually oscillates a little bit. So when excitation goes up, inhibition follows, but with a lag, right? And then it goes down, and it goes down, excitation starts following up, okay? So inhibition follows excitation with a lag. If the lag is too slow, these oscillations just get amplified until they reach some steady state. But if it follows it really quickly, then it quickly pulls it down. Okay, so that's the picture. So that's determinant, that's a trace. Determinant, I won't spend time too much time on, the determinant is psi e minus 1. Turns out the tau's time constants don't matter. Psi I minus 1 minus psi ei psi ie over tau e tau I. So the time constants don't affect the determinant. Oops. And remember, this is equal to, because psi e comma I is negative, we can write this as absolute value of psi e comma I psi sorry. Here we go. Psi I comma E minus psi E comma E minus 1 absolute value of psi I comma I over tau E tau I. So I'm not going to show it, but it turns out that that if the inhibitory neuron nuclein crosses the excitatory nuclein from below, the determinant's automatically positive. Okay, so all we really care about is the trace. The trace can be either positive or negative. So what do we have? We have a low firing rate equilibrium. Oops, oh man. Oh, sorry about that. Let's see if I can reproduce this. Okay. So to summarize, so we all basically, once we assume that neurons fire without input, they're spontaneously active, we automatically get a low firing rate equilibrium. It's pretty robust. And if inhibition is fast, it's stable. If inhibition is too slow, it's unstable. And the truth of the matter is, networks of neurons really tend to oscillate. If you try to build a spiking network with simulations, it's almost impossible to get it to not oscillate. You have to do a lot of work. So oscillations are very, very, very natural. And this is a very robust low firing rate equilibrium. And it's where we think the brain operates, okay? So even though we consider what looked like a really boring problem, which was a randomly connected network of excitatory and inhibitory neurons, it tended to have relatively non-trivial behavior, okay? Okay, so I have about 20 minutes and I want to do two things. One is, so this analysis relied on the gain functions being relatively steep. So the last few minutes, I want to address two questions. So question one, how steep are gain functions? Psi of nu E nu I. And two, how good approximation actually write this. So is nu EI equals psi EI of nu E nu I, a good approximation. And the second one is actually important because eventually, in the next couple of lectures, we're going to add a little structure. We're going to consider non-randomly connected networks. And that question becomes very important because things better not depend only on average excitatory and inhibitory firing rate. They need to depend on something else. And we need to know under what conditions they depend on something else. Okay, so first, how steep are the gain functions? So remember our equation was d nu tau e, equation for voltage. Was tau d nu dV. I'm not going to worry about excitatory versus inhibitory neurons. V is now voltage. So when I write, it's hard to tell the difference between voltage and firing rate, but I'll try to let you, it should be clear from context. Equals minus VE minus E leak plus the sum on J, Wij Gj of t. And just to remind you, Gj of t was basically from presynaptic neurons. So Gj of t looks something like this. This is time. This is axis is Gj. And every time a postsynaptic neuron spikes, it just jumps up by small amounts. And if you get multiple spikes in a row, it can go up a little bit. And this is actually on the order of 5 milliseconds. So these are times of spikes on neuron J. Okay. So what we want to know is, how big is this term? As a function of okay. So remember what we said is this is a linear integrating fire neuron. So the bigger this term is, the faster this neuron fires. So remember this is an LIF neuron, linear integrating fire. Which means when VI equals V threshold, VI resets. So a spike is emitted. It's emitted. And VI reset to EL, okay? So the more positive this term is, the more VI is going to be pushed up, okay? And the more sensitive, and so we sort of want to know how this term depends on firing rate. Okay, it's kind of there's a lot on this slide, but to summarize, we have a linear integrating fire neuron. Gj are basically every time the neuron J fires, just jumps up a little bit and falls down. And when voltage gets large enough, it emits a spike, okay? So what we're gonna do is approximate this by a constant and compute the firing rate as a function of the firing rate of the presynaptic neurons. And we're gonna consider for now only excitatory neurons that, well, be pretty easy to figure out how to put inhibitory neurons in. Okay. So let's now make an approximation. So we're gonna approximate Gj of t is equal to the sum on mu actually, let's not do that yet. Let's make things simpler. So we're going to choose, so Gj of t all right, this is a sum on mu of G0 of T minus Tj mu, where Tj mu equals time of muth spike on neuron J. Okay, so if you go back to this picture, this quantity here, these things are G0 of T. Okay, so G0 of T is this thing that doesn't last very long. It goes up and comes down. For a brief period, it's about 5 milliseconds long, and we're going to actually eventually make it shorter. Okay, so we can now ask how big is sum on J of Wij Tj of T on average? Okay, and that's easy. Basically, and the answer is, we're just going to average this over a long time. Integral 0 to T dt, the sum on J of Wij Tj of T. And that where T is large, long time. Oops. Equals the sum on J of Wij times 1 over T integral from 0 to T dt Gj of T. And now we can look at the definition of Gj of T is right up here. So this equals sum on J of Wij 1 over T integral from 0 to T of the sum on mu dt, sum on mu of G naught of T minus Tj mu. Okay. And basically what we're doing is, so G naught is just something that goes up and comes down. So G0 as a function T goes up and comes down. And we're going to choose it so the area equals 1. So the integral, that means the integral dt of G0 equals 1. So G0, for instance, might be, we'll pick, so basically that's simple enough. And so basically mu equals 1. So every time there's a spike, you get, this integrates to 1. We're going to write this again. Sum on J of Wij, the sum on mu of 1 over T, the integral 0 to T dt G naught of T minus Tj mu. Okay, this thing is 1 for each mu. One for every mu. So this is just equal to sum on J of Wij. The sum on mu is just basically N J of T over T. So Nj of T equals number of spikes in time T. Okay. And this is, so, and Nj over T, this quantity here, this is a firing rate of neuron J. Okay. So this quantity here on average is equal to this, the average value of this thing is this Wij multiplied by the firing rate, which makes sense. The higher the firing rate, the bigger this is going to be. Okay, so let's go to the next page. So we have the average over time of the sum on J of Wij, Gj of T equals the sum on J of Wij, nu J. Okay, so this consists of about 1,000 excitatory neurons. Each neuron is connected to about 1,000 excitatory neurons. And about 1,000 inhibitory neurons. So if we let K equals 1,000, average connectivity, this thing is here is about equal to 1K times WEE bar, nu E bar, plus W I bar, nu I bar. Okay. So basically, we're assuming that W's and Nu's are uncorrelated. There are about K terms in the sum. We replace W by its average. We replace, basically what we've replaced is J terms in the sum as K times the average. Okay, 1,000 terms times the average firing rate, 1,000 terms times the average inhibitory firing rate, which is kind of why we could replace things by the firing rates. Remember, WI bar is negative. Okay, so basically we know the average size of this term, but we don't really know how to interpret WE bar and WI bar in terms of physical quantities. And for that, we're going to make kind of extreme approximation, which is we're going to set Gj G0 of T equals delta of T. That's a direct delta function. So basically what we say is whenever neuron spikes, it's really big and narrow, okay? So this is G, J of T, and these are spike times. Okay? And the delta function is, it's very narrow, and the integral dt delta of T equals 0. Sorry, equals 1. So we can think of it as a rectangle. So the width is delta T, and the height is 1 over delta T. And then let delta T go to 0. So it's an infinitely high, infinitely narrow delta function. And we can ask, what's the effect of a single spike on the voltage? So we have tau dvi dt equals minus V minus E leak plus Wij delta of T. So a single spike at 0, what does it do to the voltage? We can write Vi of T plus delta T across, T minus T plus delta T. So this will be, let's say, at minus delta T over 2, at which time the, let's be a little more clear. So, and then Vi at T less than 0 equals epsilon leak. E leak. So the neuron's just sitting at the leak membrane potential, just sitting there doing nothing. It gets a big kick on the right-hand side, and that causes a big jump, okay? So Vi at, at delta T, at T plus, which means just greater than 0, equals Vi at T minus, so less than 0, plus the integral from, t minus to t plus dt. You got two terms, minus vi minus e leak plus wij delta of t times 1 over tau. What happened? Okay. So this term here doesn't make a contribution. From t minus to t plus, it's really small, so that goes away. But this, because of this term, is equal to 1. So this is equal to, so this, of course, is E leak. So this is E leak plus wij over tau. Okay. So what happens is the voltage jumps up and then decays. So when you have a delta impulse, so Vi of t, this is, let's say, t. So it goes along, it jumps up and decays. And the amount it jumps up is wij over tau. And so wij is going to equal the size of a PSP, of an ePSP. Which implies, okay, that's basically this is by definition the size of a PSP. In the absence of any other currents, a single spike, get increase and a decrease. That's what you see when you measure experiments. So that implies that wij, so this is ij, equals tau v ePSP. And so W bar E equals tau v ePSP. And W bar I equals tau v IPSP. Okay, so now basically that told us the size of the memory of the weights. So over here we had, actually it was back here. So this term is given by this, and now we know what WE bar and W and I bar are. So we can write this as the average of the sum on J of Wij, Tj of T, average over time is equal to K tau times V ePSP nu E plus V IPSP nu I. And it's 12:05, so I'm going to stop here. But we're going to use this to estimate steepness. So K is, remember, 1,000. Tau is 10 milliseconds. So we use that to estimate how steep the gain functions are. And then when we're done that, then we're going to start talking about a little bit about structured conductivity. So that's kind of it for random conductivity. I'll recap next time. So I'm going to end now, and I'll stay online for a few minutes in case you guys have any questions. And of course, I'll put everything on the website.
Then, what time are you finished?
Because